the third stage. Okay. Okay, so we will start the last stage. It's fine. Please change your rubber.
We change problem number 3.
Set. Okay, please write down the name on the board.
有位置可以坐吗？有一个位置。你有绿牌的？在这里，有绿牌。他们是什么？是 observer。然后那边那一坨啊，
有参观证的那些老师啊，
参观证都有吗？都有。我们只有发一个参观证。
有些是老师啊，
其他是老师。你确定过吗？
对。
可以过。
string and connect the center of the string to a pivot. When the pivot oscillates along with the vertical direction, the both start to collide and oscillate with increasing amplitude. Investigate the phenomena. And there are 3 key points we may focus on. Use the equation to describe the motion, and we will promote the motion mode. And this is the phenomena. When the player moves the handle up and down, the 2 balls start to swing. As the amplitude increases, the balls collide at high speed and produce a click sound. And our experiment will main focus on the high speed and the increasing amplitude. And next is the theory. And there are three parts: motion characteristic, collision and energy, and oscillatory function. And because the force on the lato is similar to the simple pendulum, so we can use the period formula of simple pendulum to analyze the lato. But because the angle is too big, that we can use the formula in the next page. So this is the period equation for the big speed, for the big angle. And next is the collision and energy transfer. When the balls collide, kinetic energy and momentum transfer between them, affecting the amplitude and frequency of the oscillation. And our analysis will all based on this concept. So this is the conservation of momentum. According to the law of conservation of momentum, the total momentum of the 2 balls remains constant in the absence of external force. And there, in the lato, we want to pay attention to the conservation is just in the horizontal direction, because the horizontal direction there is no external force. And this is the equation. And 1 and 2 is the masses of the balls, and v is velocity of the balls before collision. V prime is velocity of the balls after collision. And next is the resonance phenomena. When the driving frequency of the pivot approaches the system's natural frequency, resonance occurs, increasing the oscillation amplitude. And when the external driving frequency equals the system's neutral frequency, we can get the neutral frequency is 2 pi divided by neutral period. And when the resonance happens, we can use the period equation for big theta to calculate the natural period. So we get a natural period, we can calculate the natural frequency. And since the external driving force synchronized with the oscillation system, energy continuously accumulates, leading to increasing amplitude. And next, we discuss the damping effect in real-world scenarios. Damping affects the maximum amplitude but does not eliminate resonance. In other words, the resonance phenomenon also happens, but the amplitude didn't increase without limit. It has a maximum value. And within the main points that cause damping is the energy loss while in elastic condition. And damping ratio is the parameters usually denoted by zeta. Zeta is actual damping divided by critical damping. And this one is the definition of critical damping. When an external driving force is applied to the pivot, the system becomes a forced oscillation system expressed by this function. And we have used this function to make a simulation so we can see the relation between time and angle. And first is the measurement of damping ratio. Because damping ratio, we can use this parameter to model the oscillatory function. We use pendulum theory to calculate the critical damping. And this is the frequency. This is the period for big theta. And we change the angle and measure the experiment period to calculate the actual damping. And our damping is defined by experiment damping divided by theoretical damping. And this is our experiment data. Experiment sets up a lato and a projector to measure the angle and the stand. And this is the procedure. We lift 2 balls up to the same height and also the same angle. Use projector to measure the angle and let the ball free fall. And calculate the period and change the angle and do it again. And this is the result. the x-axis is the angle, and y-axis is the period. The upper line is the theoretical data, and the below one is the experiment data. And the damping ratio zeta is defined by actual damping divided by critical damping. And in our theory, it's experiment data divided by theoretical data is around 1.77. And we can use the data to calculate the damping coefficient. And this is the definition of damping ratio and damping coefficient. And we use the data to calculate that the damping coefficient is around 0.001042. And next is the experiment. Experiment 1, independent variable is the mass of the balls. Dependent variable is the horizontal velocity of the balls. We try to use this phenomenon to prove that this phenomenon is follow the set conservation of momentum in horizontal direction. And this is the equation of conservation momentum. And this is the procedure. We leave two balls up to the same height and use the protractor to measure the angle and let the ball free fall. Analyze the horizontal velocity by checker and change the mass of ball and do it again. This is the result. The purple one is a group of balls, and the blue one is another group of balls. And we measure the velocity before collide and after collide. And velocity times mass is the momentum before collide and after collide. And we want to discuss the two situations. One is that it has the same mass, and the other is has different mass. And this is the momentum of the same mass before collide, and this is the total momentum of the same mass after collide. And the Gauss momentum is around 0.001. And for the different mass, this is the total momentum before collide, and this is the total momentum after collide. And those momentum is around 0.0019. And we can see a result with the almost fits the conservation of momentum, the arrow made from the environmental factors. And when the mass of the two balls are different, the system is more easily to crash. Because after collision, the velocity of the two balls is different. So the next time they won't meet at the same place in the same time. So the system is easily to crash. And experiment 2, independent variable is the length of the string, and dependent variable is the period of the system. We try to use this experiment to prove that this equation. This is the procedure. We move the lateral in vertical direction and calculate the period and change the length of string and do it again. And this is the result. X-axis is the length of the string and y-axis is the period. And the orange point is our experiment data. And the blue line is the theoretical data. And we can find our experiment data is almost fits the theoretical value. As the length of the string increase, the period also increase too. And next part is a simulation. We want to simulate the oscillatory function. And based on the measurement, we can know the damping coefficient. And based on experiment 1, we can find the driving frequency and prove the natural frequency. We use Python to do the experiment, and we want to investigate the relation between the angle variation over time, because the angle can visualize the amplitude. This is the result. X-axis is the time, and y-axis is the angle. And we can see that when the time passes by, the angle becomes larger, and the angle corresponds to the amplitude. So the amplitude becomes larger. This result fits the phenomenon that when resonance occurs, the amplitude will increase. So this is my conclusion. We can use pendulum to describe the movement of lateral. And the main reason of the balls start to collide and oscillate with increasing amplitude when the pivot oscillate along the vertical direction is that resonance. We can use those equations that we have, prove that we can use our describe the oscillatory function. And thank you for your listening.
Question by opponent recorded for 2 minutes.
Okay, I'm the opponent from Team West Local. So the first question I want to ask is that do you consider this lateral system as a 2D motion?
2D motion, yes.
Which means it's only the same thing. Okay. So do you consider that when your hand is moving, the hand slacks, which is softened?
Slide is
Slack. Like the string becomes, it's not straight, it's softened.
Oh yes, the string will move. It's
Okay. So can you move to page 34? So can you again define what is the driving frequency?
driving frequency is our the frequency our hands make the lateral move.
Okay. So it is not a constant because you use hand.
Yes.
Okay. So
But in our
sorry.
experiment, the driving frequency
That's
is
the next question. In page 36, can you define amplitude?
different amplitude, and angle is the angle is this.
Okay.
So when the angle is bigger, the amplitude also bigger.
Okay, I understand. So do you consider this system as an inelastic collision?
Yes, because in the experiment once, the momentum didn't
Okay.
perfectly.
So I want to ask the next question. In page 29, so do you conduct your experiment only once?
Oh no, this is the average data.
So is this experiment done by hand driving frequency or only freefall?
Oh, not hand driving. There is like a simple pendulum that we
Okay,
this
I'm
the
sorry.
ball.
Okay, thank you.
The version of opponent for 3 minutes.
Good afternoon, worthy opponents, worthy judges and opponents. I'm the opponent from Team Go 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 Go. And the problem I'm going to oppose today is problem number 3, lateral lateral. So let me restate the problem statement. So we have attach a ball to each end of the string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the balls start to collide and oscillate with an increasing amplitude. So the reporter aims to investigate this phenomenon using the equations that they have derived to describe the motion, and they promote the motion mode. Okay, so let me simply sum up this report. So when the pivot moves up and down, the ball starts to swing. And in their theory, they talk about the motion characteristic, and they focus on the energy using the damping function. Also, they convert a simple pendulum into a vibrating pendulum, and they also use a conservation of momentum in the horizontal direction. Also, they use a resonance formula. Okay, the experiment, they use hand to swing the ball, and they use natural. Then they try to prove that their theory is right by using free fall experiment to test the damping coefficient. They test whether the conservation of momentum is correct. Okay, they also change the different mass of the ball to see whether the system will crash. And lastly, they compare the length over a period using a simulation. Okay, so the pros of the report is that they have a thorough explanation of the phenomenon and theory. Also, they have a clear experimental setup. Also, it's a precise use of Taylor's expansion in their assumption. However, I think there are some disadvantages, such as that they lack of error bar. Also, they use hands, and the accuracy is concerning. Also, they lack experimental evidence. So these are the main points that I want to discuss later. First, the report thinks that it's a 2D motion, but I totally disagree. You need experimental data to prove that it is a 2D motion in a 3D world. Also, I observed that the string slacks. So how can the work done by hand be emanated in such a simple equation? And also, they use simulation, which ignore the string slacking. And in their theory, they use damping, which already included an elastic collision. So that is also one thing I want to clarify later. Also, they need to define the amplitude because when the ball starts to collide up, they need to say what is the amplitude. Also, they shouldn't use hand because you cannot control the input of energy. So now I would like to invite the reporter up to the stage. Can I use the blackboard? So, I know that not using a hand in this experiment is extremely difficult.
Oh, I have the reason. Because the neutral frequency is different by the angle. So when the angle different, the neutral frequency is different. And if I use the machine to make the driving frequency is constant, the system will crash.
But can you change the frequency of the hand, like the machine? You can. I actually can. I can show you how to do it. You use a motor here, and you attach using a mechanical lever, and you attach this to this. So this rotates, and then it will go up and down in this direction. And this actually.
Because the public they can say that just move the calculator in vertical direction.
Sorry, this is the vertical direction. I made it wrong. Yeah. So I see it this way. Sorry. So it should be like it goes up and down.
Oh, sorry, I didn't understand the picture.
So I suggest that you use a mechanical linkage, and a mechanical linkage can change the rotation into a steady oscillating motion. Yeah, and that is, but you want to change the frequency, right? So you should do that by changing the rotational
Yes, I
frequency.
changed the frequency
Yeah.
because I want to make the resonance banana pattern. So I have to change the frequencies to meet the usual frequency.
Yeah. And I think using CAD is a good way to explore this experiment. But if you want to conduct precise ones, you should turn to the help of machine.
Oh, okay.
So the second question I want to ask is that, can you clarify how do you prove that this experiment is a 2D motion?
Because we move the lateral in direction, in vertical direction. So this is the y direction, and we measure the horizontal velocity, and this is the x horizontal direction.
Yeah, I totally agree. You try to use hand to make it vertical. And I believe that you have the ability to do that. But if for an observer like me, if you want me to believe, you need to film the bilateral in a different position. So I can see that the ball is colliding like different ways. And that is very important. You know why? Because if the bilateral is not colliding on this plane, it's going in this way, then the momentum might not be correct because you're observing in a totally different angle.
Oh, yes, I think you say it's right, but
Yeah.
according to the data, the momentum is almost constant, and the momentum, we can use the damping effect. The damping ratio is around 0.77. So I think, and combine the data and the damping
So you believe
ratio.
that your hand is like perfect like this?
Yes, I believe it's perfect. Only
I mean, it's very difficult even for a machine to be
didn't
perfect.
rotate.
So I would suggest that if you can add another camera, probably in this direction, and you can check that your hand is really a perfect oscillating thing. Yeah,
Okay.
that's my suggestion. So you talk about damping, and I really want to clarify that because in my opinion, damping is can be described as F equals minus BV. And you use damping in your model by freefall, right?
I just discussed the damping ratio because in my experiment we just need to get the damping ratio and damping coefficient. We didn't need to calculate the damping force.
Yeah, so I know that you use this equation, but my problem is that
use this equation.
you use damping, right?
Yes, I use it.
So in my opinion, damping should be a continuous force, right? It's a
Yes.
continuous. So, but do you notice that when the ball collides, the energy loss is instant? Instant. It's an inelastic collision. The energy loss is instant, and when it bounces, the air friction drag or the friction will make it again continuous damp, and then instantly it decreases again. So how can you describe this as an all continuous damping model?
All continuous. And according to the diagram you can find, we do the experiment with different angle and the chain of our experiment of damping period is similar to the theoretical. So I think the difference when we do the experiment different time, the damping ratio is the same.
Yeah, I totally agree because when the V is like here, and whenever it bounces, you can get minus EV. And that is also proportional to V. So you can use it in damping, but I think you misunderstood what damping is because this is an instant loss and this is a continuous loss. So I think my suggestion is that you separate them, like they are different things in your energy loss discussion.
I think
Do I need to say it again? Because like if two balls collide with a velocity of v, they will rebound with this is the inelastic coefficient. So maybe if you want to eliminate this effect from damping, and again consider them together. And you know how to do this? You need to like test the instant like that. And damping should be you should see like how high it can go. So that's the average damping.
You say when I use damping, I need to measure how high it goes.
Yes, yes. This is the average damping. And if you want to see how the velocity change, that is the inelastic collision.
I think although it's the inelastic collision and the damping force is constant, and because in our experiment we just need to measure the damping ratio and damping conditions.
Yeah.
Excuse me, I have to, because the timer is wrong, I think you only have three minutes.
Oh, okay.
Okay.
Okay, so I think this model probably worked in the long term, but not in a like a T.
No, you think damping is.
So I want to move on to my next question. Okay. So I think you did a simulation, right?
Yes.
So in your simulation, did you consider the string as a light stick or a string? Because a stick does not change. It cannot.
Change the shape of.
It cannot do like this, and that's what happened in your lateral like.
No, because my velocity is fast enough, so the tension is don't impact the string is always a line, straight line.
No. I think what I mean is this is a lateral system, and when your pivot accelerates downwards, the string instantly becomes soft, so the work is not done on these balls.
Become soft.
Yeah, that's what I mean.
And you think the string is become soft? Oh, okay. I think because our driving frequency is match the neutral frequency, so the resonance become the system is very solid. So the line is always a straight line. It didn't become soft.
So what you mean is if this and this they resonate, the string will always stay taut, which is tight.
Yes.
Okay, I know what you mean, but I disagree. Okay, so do you aim to consider like colliding upwards?
Oh no, it didn't collide at the upward because the velocity is our amplitude is a maximum value because our velocity don't faster than the critical velocity. So when the system didn't pass
Yeah, so
didn't collide at the upper range.
so if it's a normal circumferential flight, I know that the speed you need to get up there, this is root of gh, and this is root of 5gh. So do you consider this speed? So like the speed that can go upwards. Do you consider
Because
this?
the maximum amplitude is around there, so we control that the driving frequency, the amplitude didn't approach the maximum amplitude.
So it cannot collide here. You control the amplitude. Then you control the frequency.
Yeah, yes.
Okay. So
Excuse me, I think time's up.
yeah,
Okay, thank you.
Thank you. So let me make a brief conclusion of our discussion. First, we discussed the effect of using hands. The report said hand can oscillate in a perfectly vertical way, but I think they can control the frequency, and using a machine, like what I've said, a mechanical linkage, will be more precise. Also, they need proof to say that the lateral is actually a 2D motion that can conform to their theoretical equation. Also, about damping, the reporters say they only need to calculate damping ratio. However, I think they misunderstood the instant energy loss and after the rest of the damping. Okay, so in their simulation, they use stick, which is also different from the real case scenario, which is a string, and the string actually softens. And they say that the angular velocity is fast enough, so the string is always a straight line. But I think that even if the pivot oscillates, like, thank you so much.
Question or reviewer, the reporter for 3 minutes.
Question to the reporter. Since you mentioned in the experiment you changed the mass of the ball, right?
Yes.
And does the material of the ball change?
I didn't do an experiment, and our main focus is the mass of the ball, because when the mass of the ball is different, the system is easily to
No, I need to repeat my question. My question is,
the
what is,
material, I know, but
did it change
material and all the, you
the
mean,
material of the ball?
it's also the same, all the same,
And is the volume of that ball the same?
same. Just
Okay.
the mass different, other is the same.
Okay, and how do you change the mass of the ball?
And I buy different balls, and but the box value and the material is the same.
Okay, thank you. Since the reporter thinks he can generate a ball in different masses, but however maintain the same size and same material, the reviewer thinks it's impossible. Thank you. Question to the opponent. Since you asked him about the, you asked him if the string is a stick, right?
Yeah.
Can you predict if the phenomenon happened when it is a stick?
I think they predicted the phenomenon in their theory because they assumed that it's a stick. But if I were to predict if it's a line, I would say that the oscillator do positive work when it moves upward, but do no work when it goes downwards.
Okay, thank you. Question to the opponent. Can you can you predict when the elasticity of the string change? What will happen? Like the frequency?
Elasticity of the string.
Yes.
I think string just generates the tension. So
It
the
doesn't
string.
matter?
Yes, it.
Okay, thank you.
That doesn't matter. The string, we just need to discuss the string is always a straight line, or became soft during the experiment. We didn't use the elastic or inelastic.
And can you make sure the length of the string always maintain the same?
Yes, the length of the string is always the same.
And did you use tracker like to prove it?
I use tracker to analyze my data, but I didn't prove that the length of the string
Okay.
is the
Thank
same.
you. Question to the opponent. You keep saying that suggesting using device to oscillate the ball.
Yes.
And why do you think it will cause deviation? If we use it?
Because in your hand model, you cannot control whether it's a 3D or 2D model, and plus the frequency cannot be
Okay,
quantified.
time's up. The question of reviewer for 2 minutes. Okay, time's up. The reviewer takes the floor for 4 minutes.
Honorable judges and fellow competitors, I am Dennis from Team Excelsior, and today I will be reviewing number 3, Lato. This is the problem statement, and today we will focus on how different parameters affect the amplitude variation, since the problem statement mentioned increasing amplitude. And also, next, the review of the report. They just use the theory of motion characteristic, conservation of a momentum, and resonance phenomenon. And the experiment they did is the mass of the ball and the length of the string. The reporter did a great job explaining the physics and the collision very well, and they had a clear device diagram. However, they didn't analyze the effect of different collision conditions, like different material of the ball, and different material of the string, and different volume of the balls. And they also didn't have any qualitative explanation and lacking error analysis, since the TYPT theory line and the experiment data doesn't fit. And the lack of parameters, and the reporter also used hand to do the experiment, so it will cause a lot of error. And for the review of the opposition, he observed that the reporter lacked the experimental setup, and a lot of deviation is discussed. However, he didn't discuss the lack of parameters and boundary limit of amplitude. This is the manual error, and the opponent think they should use a device to do the experiment, and the reviewer agrees with the opponent. There might be manual errors using human hand to conduct the experiment. And next is the tightness of the string. The opponent wants to know if the string length will maintain the same, and the reporter thinks it will also maintain the same. However, the reviewer agrees with the opponent, but the reviewer suggests the reporter to use tracker to track the length of the string to really make sure it really maintains the same. Next is the question of reviewer. Will the different elasticity of string affect the oscillation motion? And the reporter said the string just generates the tension, so it doesn't matter. And the reviewer also asks that since the reporter has changed the mass of the ball in the experiment, and does the material and the size of the ball change? And the reporter thinks it are all the same. However, the reviewer doesn't think they can change the mass of the ball, maintaining volume and the material at the same time. It is impossible. Last is the point missed. They did not discuss about different string material and different material of the ball. And the angle of starting position is not answered, since the reporter didn't mention it in the PowerPoint. And the error analysis. The reviewer strongly suggests the reporter to track the length of the string during the experiment. And they failed to discuss the boundary limit. The reviewer really wants to know what is the limit when the ball is not able to collide. And last is the theory limits, energy conversion. And last is the experimental setup. The reporter used manual versus devices. And the opponent wants to know that
Okay, time's up. Concluding remark of reporter for 2 minutes.
This is the concluding remark of Lato. We consider the movement of the Lato is a 2D motion, but I agree with the opponent that we should set 2 cameras to show that it's a 3D motion. And the reason that we use hand is because the natural frequency changes while the angle changes. So we have to change driving frequency to fit the neutral frequency. But I think the opponent give me the suggestion that this setup is good. And definition of amplitude is the vertical height that does not vary from the original position. The damping is caused by a continuous force, but we measure the damping coefficient in the period. we use it in the whole period. And that is we only make the ball collide one time, and so every time the ball is the first collision, so the damping force is the same. And the string will be soft when amplitude reach to a height. We do the experiment when the balls haven't reached to the height. So before the amplitude match the critical value, and the string didn't become soft. It's like a stick before reach the maximum amplitude. String and reviewer asked me about the string material. I said that the string just generate the tension, and we didn't need to consider if the string is elastic or inelastic. We just need to discuss the string didn't change the shape or became soft. And I say that we do an experiment before the string became soft.
Thank you. Question of the jury. Any question?
So this problem basically is force oscillation, right? So you try to force some external force to make this system rise the resonance. But I didn't see your result because you showed some data previously. Can you show me what the improvement of the resonance?
When the resonance happens, this is the neutral frequency and neutral period, and we measure the neutral period in the experiment tube there.
Period.
Yes, we use the neutral period to calculate that. At this time, this is correspond to the neutral frequency, so the resonance happens.
So how do you know what the natural frequency?
We use neutral frequency is 2 pi divided by neutral period.
Okay. Then what the natural period?
And because we put the data into the simulation, we can find the angle become bigger, and so the amplitudes become bigger. And so I think when the amplitude become increase gradually, and this is the resonance phenomenon.
Yeah, that one. That's the angle variation, right? But I didn't see a dramatically increasing of the amplitude. It's just gradually increasing. So how do you say that's the resonance phenomenon?
If this is not the resonance, the angle will almost the same, and the angle become bigger gradually. So I think this is the resonance.
So what's the other opinion?
Can I speak first?
Sure.
I would like to explain this phenomenon in an energy perspective. When the ball, can I use the blackboard? When the ball, I think the lateral is like this, and when it goes down, it's like this. So if you do the same, when you exert upward energy, and that can after collision, this will go wider.
So
So I think the angle can be transferred into potential energy U. And that is the result of the increasing potential energy. And also the increase of total energy.
So how does that relate to the resonance?
I think resonance is the first part, because it needs, this only works when the force, when the periodic force is in line with this system. It cannot exert force when it is up here. It needs to be like this and exert force. And again, it exerts force, exerts energy, so the energy becomes bigger.
And the reviewer uses that. The reviewer thinks like when originally the ball will be like here, and after collision it will be moved to here. And the reviewer thinks it's because of effective acceleration. Because when the ball is at this position, the effective acceleration will be very big to take the ball down. And when the ball is at the bottom, the gravitational effective acceleration will be very small. So it could make the ball up. And like after those collisions, it will start to have an increasing amplitude.
Okay, thank you. Any more questions?
For reporter, you show again the natural frequency formula or period formula. You have several terms. How many terms did you include in your calculation? This Taylor expansion is mentioned. Yeah, this is a dot, right? So how many terms do you include in your calculation for this period?
I calculate to the I use Python and Python calculate to the 10 to the 10, and this to the 10. The sine.
How do you justify that you calculate up to 10 terms, then that's enough? If you have a figure theta 0, right, you should include all 10, right?
And we calculate to the tens, and the sine theta is small enough to ignore, and not ignore. It's small enough, and after the 10 we can ignore.
How about the 90 degree? If it's 90 degrees, always 1.
90
You cannot ignore it.
degree. We did this out the ball free fall, so there is no 19 degree. Yes, at 19 degree we put the ball free fall.
All right, any terms?
Time's up. Okay, so you guys have the score. Thank you. Please show the score of reporter. 5, 4, 5, 5, and 8. Next is the score of opponent. 7, 7, 7, and 6, and 8. Next is the score of reviewers. 7, 7, 5, 5, and 7. Okay, I'm glad to announce the this 5 will be the end. So, any comment or suggestion for students?
I think this one, in my opinion, they're doing better than the previous one. At least I understand most of the discussion. So this problem, I think, is hard. It's very hard one. First of all, you've got a lot of controlled condition. You have to be very careful. Also, when the angle becomes big, it's sort of not linear. It got, I don't know, the motion becomes, I mean, simple harmonic motion, the angle is small. So the equation is more regular, but when this gets big, it may have some different pattern. That's what I think so. But I don't ask for that. That's too difficult. I give better score this round. Just I understand you guys are talking about.
Okay, thank you. Any more comment or suggestion? Okay, maybe I will give some suggestions for all of you because I think the debate, the tournament, the fifth fight is most importantly. You have to discuss based on the reporters, the report, the slide on their information or the experiment or even the theories. I think most of you just discuss on the board and for example, maybe our jurists, we're curious about some part of, for example, the theory, what's the equation of theory, or I hope to see what's the code for your simulation. But I think most of you, I think more than 60 or 70% of the time you just discuss for your own opinion, but not based on the research on the reported research. Yeah, that's my suggestion. Okay, thank you. 好，那么这场就到这边结束了，谢谢大家。